Hi everyone, with my colleagues Burak, Rushil, Prakar, and myself Efe. We're here to present our insights and progress regarding our dissertation work we call The Gap in the Cloud. Nowadays, we encounter these conceptions and growing concerns more than ever, expressed via popular buzzwords. We started tracing the emergence from the point zero. Throughout the history, as you can see, various modes of repositing information were discovered and developed. Tracing down to the fundamentals necessary to be able to reposit a unit information, we found out data, space, and energy are the three preliminary constituents, no matter what the medium is. And we question, how are they interdependent on the other? Data are raw materials from our environment, forming a hierarchy as data, information, then knowledge, and ultimately a wisdom. Like bricks, data hold value when used or stored, and classifying it is rather complex in terms of raw and processed forms. Structured data are like libraries, while semi-structured ones are a mix of structured and unstructured elements. But today, the 80% of the unstructured data are driven by social media. Though it is relative, data can be subjective and objective. One person's primary can be another's secondary data. Imagine a unit data, byte, as a water droplet. In this manner, it is estimated that the data we'll generate next year will be equal to 175 zettabytes, or within this analog, 175 times of the Gulf of California. And the processing of that amount is enabled by what we attribute today as the cloud phenomenon. It is invisible to our senses and therefore largely ignored, but it has a deeply rooted, isolated physicality somewhere else. And therefore we say data matter and have matter. Imagine data processors as a black box. With transistors doubling every 2 years, the hardware shrinks, but this increases the heat production per unit. And despite miniaturization, our demand for computation grows. As you can see, we created 5 exabytes of data from the dawn of civilization to 2003, but now we create that amount every 2 days. On the left-hand side, you can see the first computer filling a room. And on the right-hand side is the humankind's fastest computer to this day, called Fugaku. Although the computational capacity has increased enormously, the energy and space requirements to process data stay comparable. But how do these billions of data processors are linked to another? These processors we have exist with the help of auxiliary components under the domain of data centers that also require a significant amount of energy supply to perform their corresponding tasks. Even today, if you only consider the GPTs we are all somehow interacting, these facilities have oftenly unaddressed, yet highly critical impact on global energy consumption rates. This increasing demand leads data centers to seek for more efficient, stable, and reliable resource management strategies. The trilogy of these individual domains we initially extracted and their intersections hinted us about the hidden potentials of such wide domain. Through the literature and studies, we questioned data center building practices along with the potential value this typology can have in various contexts. So the contextual adaptation, waste energy utilization, and spatial hybridization were the 3 interrelated tangents we extracted as potentials way forwards.
Data journey starts from connected devices like our smartphones. It first travels to edge data centers located close to users, providing quick local processing and reducing latency. Then it moves to hyperscale data centers far from the urban context for further processing. Contrasting the last decade's hyperscale data centers, current development like 5G and IoT in our daily life requires low latency computing in the urban context where the end users are. While the location of data centers in the city center is determined according to multiple parameters, buildings are either retrofitted or purpose-built facilities are constructed depending on the availability of the building stock. However, due to the size of the plot and existing building, building stocks, expansion and scaling are few of many addressable challenges in the urban context of London. In relation with the projected demand, rather than the embedded Frankensteins around us, how can data centers be positioned in mutualistic manner? Additionally, from traditional monolithic to the potential seeking modular approaches, how responsive are the current data center building practices to supply the ever-changing computational demand? Gathering our observations, we superimpose these spectra to be able to plot our inferences. Though the critical aspects from the case studies, we realize the monolithic architecture ends up serving only as a shelter. While its modular counterparts promise scalability, this only stays at the machinery level, which sustains the inefficient space utilization. In the urban fabric, results more often end up overscaling, failing to adapt to the temporality. We realize a scalable, adaptable typology, which is positioned in the urban context to provide low latency computing, is missing. In addition to our inferences from existing discourse, with our initial insights, we propose a third dimension to craft our domain of interest, asking, being pulled back to the cities, how can a collaborative interface can be initiated between data centers and the public? We question a potential intervention point wherein we challenge all three extents, directly informed by the context. Looking at Europe, London houses more than 300 high-density computing data centers, strengthening its status as a global data hub. We plotted the data centers and the allotments areas for the cultivation per person, and a stark contrast appeared. Although these zones have high data processing and significant food consumption, they have low food production capabilities. Therefore, we question, how can we generate a scalable data center typology in London to define a public interface via utilizing its excess heat for urban cultivation?
This stage marked the transition to our strategy, both spatial and material, interrelated. We studied fundamental components of a data center that define it as a mission-critical typology. We prefer single-phase immersion cooling for our IT tanks through our quantitative analysis. These tanks host the data flow and computation. Therefore, they are the main heat sources. Heat exchanger supplies a medium for heat exchange as hot liquid from the IT and fresh air from the outside. On the current day scenario, the resultant heat in the form of hot air is released to the atmosphere. This very point is our main intervention point. We purpose a hybridization that will utilize the waste heat in the form of productive public good, which is cultivation. Studying the technical information available, the challenge appeared as, while the cultivation units require stable heat conditions, the heat supply amount from the IT fluctuates up to 40% in between the day and night because of the urban data activity. To enable and maintain the functional hybridization, we developed a material system. Phase-changing materials as a passive thermal regulator, not commonly seen in the industry, PCMs, phase-changing materials, are designed to store and release thermal energy via the latent heat efficiently and in a customizable temperature range. We have studied multiple types and selected the hydrated salts according to their respective metrics. More specifically, calcium chloride hexahydrate, where we can see its formation on multiple phases. PCMs need to be encapsulated, and the common practice is via spherical polymeric shells. This know-how paved the way for additive manufacturing potentials of these encapsulated shells. Accordingly, we introduced triply periodic minimal surfaces in order to introduce an effective porosity. The configuration addressed the TPMS surface to subdivide the volume into two separate subvolumes for both media, the circulating hot air and the storing the PCM. We've studied various configurations starting from the very types. We performed CFD simulations inputting the data coming in from the waste heat. We observed that while diamond and gyroids configurations perform better to redirect the hot air, the pockets generated within the other two supplies potential heat traps. And to control this level of porosity, we've implemented a parameterized gradient, as well as a blending operation to further combine multiple advantages of one on the other. Gathering the capabilities within the material system developed, we question how can the morphology be adapted for further customized to the space it inhabits. Combining a matrix of space and energy inputs with related equations, we achieved adaptive panel configuration utilizing the blending and grading capabilities that effectively traps the flowing hot air. A proof of concept experiment was conducted to assess the impact on real-life scenario. The main goal was to measure the PCM's contribution to temperature changes with the adjacent volume. Here you can see the experiment setup that we had tested. Records were taken and temperatures were measured with the help of multi-channel thermometers and thermal imaging cameras. If we consider the temperature domain for the cultivation area between 25 and 28.5 degrees Celsius for comparison, in the experiment without using PCM, the temperature changed from room to 28.5 and back to 25 took an hour and 10 minutes. However, with the PCM, it took around 4 hours and 25 minutes, which is almost 3 times, demonstrating that a TPMS surface filled with PCM can effectively regulate the heat around it. Additionally, the experiment revealed that the PCM material's transparency changes with the phase transitions, presenting an additional architectural potential. Thanks to the PCM infill TPMS-based shell, an interface has been established between heat exchanger and the cultivation, ensuring the new set of spatial relations. As we move forward, the functional and volumetric necessities appear to represent a packing problem, where we question a reconfigurable and adaptable space-making strategy.
Instead of voxels, we realized we need geometries, more efficient surface to volume ratio to increase potential interface configuration. Hence, we explored different spaces, space filling of polyhedra, and picked the truncated octahedron. Mainstream volume was further detailed as multiple space-making units. According to the required interface configuration, routes were defined to guide the modular assemblies. Each space-making object unit of the modular assembly can be adapted as per its assigned architectural program. To pick up a pilot district in London, we mapped down various data like network bandwidth, location of ICT sector, finance sector, along with population density and more. We weighted based on multiple criteria like public interface and computational demand, and based on the output of information, Whitechapel has been selected for the experiment. The modular assembly was informed by environmental condition, whose data was extracted from the site and optimized using multiple objective algorithm. The modular assembly was achieved with optimized generator and desired metrics. The cross-functional mapping of modules were optimized according to ensure the efficient resource, program, and user distribution. The section illustrates the integration of IT system, heat exchangers, and cultivation units. Here you can see the bits and pieces of the generated output. We conducted a post-assembly CFD analysis, and the TPMS panels performed as expected, allowing the regulated permeability. Here you can see the pipeline we crafted at the stage of our registration. If we adjust the tiles, such as context, the information flow within the pipeline adapts to generate various assemblies, depending on their various scenarios and context. During the Climate Matter Week, we witnessed the urgency of addressing the resource intensive practice, near-futuring challenges, and potential intervention points. As part of our registration, we invite you to identify your own gap in the cloud above. Thank you.
I don't think you and I should comment on this because
thank you for that fascinating study. I think this issue of space and heat dissipation is going to be increasingly an issue, not just for data centers, but is going to provide us with some strategies for a warming world. I mean, obviously, I don't come from the computing background, but there are a couple of things that I just want to draw reference to. I was fascinated by potentially maybe the work of Kevin Slavin on the role of algorithms in cities and, you know, the proximity of these spaces politically, specifically with relationship to the economic market, and or the banking systems, so that they're gaining microseconds advantage over competitors. But then the other part, particularly when you're starting to explore the geometries, was this may not be your thing, but this is the thing that started to fascinate me, which is there are a number of different kinds of animals, species, particularly social animals, that live in burrows, which also become hot and sticky, and that there are different strategies, dynamic strategies, through which organisms such as termites and I think African mole rats not only adapt themselves but also change the structures of their burrows. And I would be very interested to see how your strategy compares with a number of different organisms that are used to changing the relationship between surface area and space. Just to get a sense of the variety of tactics, because your calculations are under a very specific set of conditions. But I'd be interested how applicable, how robust your insights are, and whether you can pick up other principles by maybe having a look at some of the links with biomimicry, not to copy, but really just to kind of have a think about the range of parameters that you could incorporate into your work. So I think it's really fascinating, and I think we're going to have to deal with this critical issue. And I think the last thing, to go back to the biological really a bit, is when we think of organisms computing, they don't centralize. It's a very distributed form of work and thinking, to a point where we have brains, but we also have neural networks. And again, I think kind of looking at how decentralization or kind of more distributed forms of location of the work that's being performed by the computation, so that for poorer areas of the city rather than the richer banking spaces, can we actually tackle kind of urban heat island effects and stuff like that, by reorganizing some of these spaces. But I think it's absolutely fascinating. I think it's a core principle, and I think you could take it in a lot of different directions. So you've got my brain kind of working and overheating over time.
Something a reference I don't know if I've given you before is a 1965 poem by Brattaghan called Machines of Loving Grace, which were dreams of cybernetic futures, and that humans would be looked after by machines of loving grace. And it became a kind of more critical phrase for a series, I think, of 3 films made in 2010 or 12, somewhere around there, specifically about London, the invisible algorithmic processes of cities. A very non-technical film, but a kind of cultural critique of invisible algorithms. So I think that adds potentially another kind of dialogue. It's not something you can use to prove or disprove anything, but it helps maybe to situate the cultural implications of the work you're interested to do.